The human brain weighs about 1.5 kilograms of tissue, but inside it, 100 billion neurons and 1,000 billion connections between them. Years of research. And what we still don't know is worth more than what we know. When you learn something new, a skill, a language, you feel it. Something changes in you. But exactly what changes and where is a question neuroscientists are still trying to unravel. Professor Yaniv Assaf from Tel Aviv University decided to answer this question. Not in controlled lab conditions, not with boring experiments, but with skills from life itself. It all started with a video game. Professor Assaf's first study was built around need for speed. They gave subjects who played the game the Monte Carlo track and a Porsche, and they had to play repeatedly to finish the lap as fast as possible. From the repeated play, the shape of the track itself solidified in their minds, even though they had never seen it. If we asked them to draw it, they really could draw it with very high accuracy. The subjects were scanned before they started playing and again after. Not during the game, only before and after. What they found surprised even the researchers. Within minutes, not hours, not days, the microstructure of the hippocampus changed. The insular cortex changed. The brain doesn't wait. It starts working from the very first moment. When you become an expert, your brain doesn't just grow, it also shrinks. Certain areas grow in volume, others decrease. The brain removes what is redundant. It streamlines, it sharpens, it becomes a machine. But how do we know this happened? How can we see expertise? Not just in structure, but in action.
Hello, my name is Professor Yaniv Assaf. I'm from Tel Aviv University. In terms of scientific exploration of learning, you need to do, theoretically, a very controlled study. And the controlled study is that you control everything that happens to the subject. And so it has to be in a controlled environment, and the task itself that it performs needs to be very clean in terms that if you want to measure learning or plasticity, it has to be a very clean procedure. One of the most investigated procedures in behavioral psychology is finger tapping. It's a motor sequence learning. When they give you a sequence of tapping on the fingers, the first, the second, etc. So there's a sequence. You need to memorize this sequence, and then they measure your reaction time and your accuracy. This is nice. It's obviously short-term memory and there is learning involved in that, but its relation to our real-life learning is quite limited because this is not something you usually do and you need to learn over time in your life. In your life, you need to learn other things that are more complicated and engage different cognitive domains.
It works, but it's not real life. Assaf sought to investigate learning as it actually happens, with motivation, with internal reward, with meaning. He recruited volunteers and sent them to learn something they wanted to learn. An MRI scan before, 2 to 3 months of training, another scan after. Brazilian Jiu-Jitsu, a full contact sport. No distance, no protection. Just body, brain, and trust. What they found in the brains of people who learned Jiu-Jitsu changed what was previously thought. First, the motor system, as expected. Second, strategy and logic. Planning areas that are active exactly as in chess. Because Jiu-Jitsu is chess played with the body, 2 or 3 steps ahead, always. And third, the most surprising of all, the amygdala, the center of emotions. It changed. Jiu-Jitsu is an intimate sport. You are attached to another person completely, and there is trust in it. Some of the subjects arrived with a history of anxiety and trauma. They said the training changed their lives. Now there is data showing they are not imagining it. Ronnie is a PhD student in the lab. Her question: what happens to the brain when a person learns to program?
So I'm a PhD candidate at Professor Yaniv Assaf's lab. My project is part of the Big Plasticity project, and we focus on what changes in people's brains when they learn to program in Python. So basically what we did is we have a big cohort of programmers and people who have never touched code in their life. And we started out by just looking what's different in their brains, how their brain connectivity structure is different between those two groups. And then later on, we took people who've never programmed and tried to see what changes in their brain after they go through a programming course. So the idea originally was to try and characterize what a programmer's brain looks like. And that's what we set out looking for. But what we actually found was that programmers and non-programmers seemed more similar to each other than people who are halfway there. So the people who know how to code but aren't actually programmers seem to be a lot more different from the non-programmers than the experts were. And that was actually, for me, the most interesting part, because basically what we could see was that the process of learning is not linear. So they started out with a lot of change in their brain, and then their brains kind of settled back into a different pattern, but into a more organized pattern that's more similar to what we are at the baseline. So the idea was that when we looked at the brain structure, at the size of areas in the brain or at the microstructure of those areas in the brain, we saw that they kind of went back to being similar with experts. But when we looked at the connectivity, at how those areas connect between each other, we actually saw that we have a large growth in connectivity, a very large difference in connectivity when people started learning. And then as they continued learning, those connections went back to something that's more organized, but different than original. So what we saw was that people have a very dramatic change when they start learning. Their brain wiring goes nuts, changes a lot, has a lot of big differences. But when they settle into an expertise, all those extra connections and all those different connections kind of disappear again and calm down again, and their brain settles into a new pattern and new organization that is more relevant for experts. A lot of the time when people think about programming and what areas of the brain are associated with that, they might either think about logic and mathematics, or they might think about language. And a lot of programmers that I talked to thought it would be very obvious that learning to code is very similar to learning a new language. But what we actually found was that it's neither here nor there. We don't see specific changes in that area or in that area or in other different areas that are associated with programming. And instead what we see is a very big change in the connections between them. So it's not that your language area or your math area become more specialized, but it's the expertise in programming actually comes from the connection between those areas.
Amir, another PhD student in the lab, chose a different skill: music. His research began with the question, is it possible to know from an MRI scan if someone is a player? And what instrument do they play? Together with composer Adi Rennert, he built a unique musical piece. A piece that moves between different styles and was recorded with top musicians. 17 minutes of complex music. And he examined how the brain reacts. The brain of a musician and the brain of someone who has never played react differently, even when they are doing nothing, just hearing.
My study is part of a big research that we do in the lab, and that we try to look at the neuroplasticity, at how the brain change through different experiences. And I took this theme and focused specifically on musicians and music learning and music practice. So one of our purposes in my study is to see if we can understand only from the brain scan what is the musical background of a specific individual. So for example, we want to take a random subject from the population and to see if we can understand only based on his brain if he is a trumpet player, if he is a pianist, or so on. We try to understand what really affects the performance of one that study a musical instrument. And we saw that it's really depend on the individual. There were some participants that barely practiced at home, but were really good in learning this skill from scratch, and others that were trying over and over, and no matter what they did, they didn't really improve. So the inter-subject variability is really important, especially in the earlier stages of learning music as a skill.
Yuval, a master's student in the lab, works with 200 subjects: climbers and jiu-jitsu fighters.
So basically in my study I was working on existing data and of participants that were participating in the learning classes. During these studies, participants come to the MRI machine. They are scanned before doing anything, some structural scans as well as functional scans. In these functional scans they are shown two videos. Both of them are short videos, around 3 minutes. And one of them is related to climbing and the other is related to Jiu-Jitsu. Both of them are the main learning skills that I focused on my research, followed by around 12 weeks of training in which they participated weekly in classes related to their chosen skill, which is either climbing or Jiu-Jitsu.
When you watch your own skill, your brain synchronizes with the brains of all the other people who have that same skill. The motor areas, the planning areas, the cerebral cortex, they pulse together. When you watch something that isn't yours, this synchronization disappears. This means the skill didn't just change your brain from the inside, it changed the way your brain reads the world from the outside. A climber's brain sees a climbing video and knows exactly what is happening there. Doesn't just see, feels, simulates, lives it. And this, exactly this, is the professional brain. After years of research, what is taking shape is a new idea. For every skill, for every profession, there is a neural fingerprint. Not a specific area, but a pattern, a network, an organization. The models they built identify these patterns with an accuracy of 80 to 85%. The brain of a musician, the brain of a programmer, the brain of a jiu-jitsu fighter. Each one a bit different, a bit unique. And what we learned, perhaps, is that the human brain is more flexible than we thought. That everything you learn, even if at the time of the current study you are just starting, already etches itself into your structure. 1,000 subjects, 5 years, a grant from the European Union. Different skills. One question: what happens to the brain when we learn something we love? The answer is still incomplete, but the direction is clear. The brain doesn't wait for permission. It doesn't wait for the 100th practice session. It starts changing itself from the very first moment.